For those of you who are unfamiliar with our organization, Hamptons Observatory was founded roughly 17 years ago with a mission to provide free, year-round, family-friendly educational events that focus on science and the natural world. After the presentation, please visit Hamptons Observatory website, which I believe Donna will post in our chat in just a few moments, to view our future presentations, join our email list, or perhaps even donate to ensure that we can continue providing these incredible opportunities for everyone. If you feel inspired by tonight's presentation and you live locally in New York, which I know some of you do not, please visit Suffolk County Community College, where you can begin your journey into a scientific career at one of our 3 campuses in Brentwood, Selden, or Riverhead, or from the comfort of your own home through many of our online offerings. And as I mentioned earlier, as we begin tonight's presentation, I ask that you keep your microphones muted, but please feel free to post questions in the chat and at the conclusion of the presentation, we will do our best to address all of your questions. Tonight's presentation, really looking forward to it. Dr. Paul Andrew Mayewski is an internationally acclaimed glaciologist, climate scientist, polar explorer. He's the director of multi-disciplinary Climate Change Institute and distinguished professor in the School of Earth Sciences, School of Marine Sciences, School of Policy and International Affairs, Business School and Law School, all at the University of Maine. Paul was born in Scotland, where he was introduced to hiking very early in life. He has thus far led more than 60 expeditions to the remotest polar and high elevation reaches of the planet and received several prestigious national and international awards, such as the inaugural Medal for Excellence in Antarctic Research from a field of 45 countries in all disciplines, the European Geophysical Union Oscar Medal, an honorary PhD from Stockholm University, the International Glaciology Society Seligman Crystal, and the Explorers Club Lowell Thomas Medal. His contributions to science include the discovery of abrupt climate change driven by atmospheric circulation, human impacts on the chemistry of the atmosphere, impacts of climate change on humans and the ecosystem, new methods for ultra-high resolution ice core sampling, pioneering ice core climate calibration techniques, the history of human-sourced toxic metal emissions, and the application of past and present climate research to modern-day challenges such as health, climate prediction, and climate education. His achievements in exploration include leading teams into uncharted regions of Antarctica, many thousands of kilometers of polar surface traversing, and numerous first ascents of mountains, all to gain scientific knowledge. Paul has started and led several prominent research projects. Most notably, he's the first person to develop and lead highly successful interdisciplinary climate research programs at the 3 poles, Greenland 25 and US institutions. The International Trans-Antarctic Expedition, which is 21 countries, and the Himalayan Tibetan Plateau, most recently the National Geographic and Rolex Perpetual Planet Mount Everest Expedition, which includes 34 international researchers that attained 3 Guinness World Records. He has more than 500 scientific publications, hundreds of popular and scientific lectures worldwide, 2 popular books, The Ice Chronicles and Journey into Climate, and has appeared hundreds of times in media such as the New York and LA Times, Nova, NPR, BBC, and multiple CBS 60-minute shows, and the Emmy award-winning Years of Living Dangerously. With that, I welcome Paul Andrew Mayewski. Thank you, Paul.
Thank you so much, Sean. Wonderful to sort of see everybody. This is certainly an interesting evening to have this particular presentation, because those of us who live in the Northeast, and certainly the person who joined from New Zealand, we're all experiencing some rather exciting weather that changes literally day to day. So I'll be talking, of course, about climate, which is the mixture of weather over months and a couple of 3-4 years. But I'll not only take you on a journey through climate, but I'm also going to take you around the world based on our expeditions of the last few decades. And the goal of these explorations has included exploration into many different places previously unvisited. We'll talk about a little bit of the adventure going along with it, and then I'll try to focus in on the discoveries that we've made and what sort of relevance they might have to where we are today. There we go. There are many colleagues and students who've been involved in the research that I'm going to talk about, and many different federal and private organizations that have funded this research. The institute that I direct is now 50 years old, making it one of the oldest, certainly in North America. We look at the physical, chemical, biological, and social aspects of climate change. And we are probably best known for looking at past climate, but we also do quite a bit of work and have developed a lot of software related to present climate. And much of this is dedicated to understanding future climate. But for this evening's presentation, I'm really going to focus on past and present climate to give you a few snapshot views of what we're doing. Sorry, I'm having a little trouble with the mouse going here. Our institute does many things. We're quite large, but I'll focus primarily on ice cores, cylinders of ice that we recover from all over the world where the red dots are. It's the most robust way of understanding a whole series of components in the climate system. Literally everything that's in the atmosphere can eventually be captured in an ice core. If you look to the left side here, you see an idealized ice core and a large ice sheet like Greenland, or sorry about that, it's jumping around here. Like Greenland or a high alpine glacier. And of course, we can monitor temperature, we can monitor solar variability, we can see sea salt that comes off storms that tells us about the strength of the storm, agricultural activity, volcanic activity, and also human emissions from everything from industry to mining. Well, I was fortunate enough, as soon as I graduated from college, to live a dream that I had wanted to for those early years, and that was to go to Antarctica. Antarctica is a spectacular place, 1.5 times the size of the United States. Average ice thickness about close to 8,000 to 10,000 feet in thickness. Don't know why this is jumping around. I apologize. And that red arrow shows you the first flight that many of us take to the Antarctic from New Zealand. We eventually end up making our way to a region called the Ross Sea. In the background there, you see Mount Erebus, a 15,000-foot high volcano. You see a little bit of smoke coming off the top. It's literally always steaming out a little bit of hot water and sulfur. And in the middle, you see a large white sheet. That's the Ross Ice Shelf. It's about the size of Texas. This is just a tiny corner. The portion of the ice that's out of the water is several hundred feet thick. And these little squares and various other geometric features you see are icebergs that are the size of city blocks. So Antarctica is an immense place. Scale is just completely different, and there's really little to be able to judge it from. The place that many of us start first is McMurdo Station, the U.S. station. And if you look at the blue circle, you'll see it's very close to a series of valleys, which, although the ice is very thick, there's a threshold that prevents the ice sheet from coming into those valleys. One of the things that's particularly exciting about this area is that within about 25 or 30 miles of the station, you can go out and test your equipment, and you can visit Shackleton and Scott's old huts from the turn of the last century. You can see the insides of the huts and the places that they slept and worked in for 2 to 3 years at a time. You can see Dr. Wilson, who was one of the big scientists involved in one of those expeditions. This is his laboratory, all pretty well preserved. In fact, so well preserved that the emperor penguin that he was working on when he left and eventually perished on his way to returning from the South Pole is still there. You touch the penguin and he feels like a live penguin. You go into the mountains, you begin to see these very strange rock features. These are places where they're not covered by ice. The mountains are high enough right here, and they've been sculptured by the wind. And the best estimate is that it takes hundreds of thousands of years to create these sculptures. And by the way, that was me when I had dark hair and a lot more hair too. The other thing that's particularly interesting is the fact that there are seal skeletons along portions of this coast. These are juvenile seals, and the reason that this one, you see the bones, is because it's been wind eroded. You turn them over, and again, the fur on the underside, which is protected, feels like a modern day seal. What's particularly remarkable about these seals is that after radiocarbon dating, it turns out that they're thousands of years old. So one gets the feeling between the preservation of the huts, the seals, how long it takes to sculpture the rocks, that this place is absolutely timeless. We spent a few seasons there, and then I decided that we would begin to look into other parts of the Transantarctic Mountains that had never been explored before. The circled area here called Northern Victoria Land, relatively large piece of property. And in order to travel around, we had snowmobiles, 2 snowmobiles, for a total of 4 sleds, 4 people, and we went on several 100-plus day traverses across the region. The bamboo poles were to be used in times when we had whiteout so that we could make our way to where we would go, well, home certainly. Heavily crevassed, very large crevasses. You have to be very careful moving around here, but it was just a beautiful and spectacular place. Spent all of our time when we weren't traveling, setting up Scott tents. These are the same tents that Scott used, just a little bit larger. Spectacular views, amazingly wind-resistant tents, despite the fact that the winds can easily go up to 60 or 70 miles per hour. And in many cases, the temperatures are close to -30, -40 degrees centigrade. As we went around these areas where the mountains, again, were large enough, there were small glaciers that were flowing off the mountains. And as we got closer and closer to these mountains, we realized, based on the debris in front of them, that they had retreated from this debris, and the debris looked pretty fresh. So we began to think that maybe Antarctica was not quite as timeless as we thought. Now, keep in mind, this is in the 1970s and early 1980s. The assumption was that Antarctica was far away. Nobody really worried about it very much, and everybody assumed that it would never change. This was the beginning, along with what other people discovered too, obviously, of realizing that even an unbelievably cold and large place like Antarctica, that literally has its own climate because of all of the snow, could actually change. In addition, when we were traversing on several of these trips, we would carry at least 2 spare Scott tents at 2 people per tent. We had new tents. The one in the background, that orange one, is what they look like when they're new. And the one that's closer to us is one that has been out in the sun for about a month. They ended up losing their color very, very fast. And in another couple of weeks, it's almost as if a cat was scratching the material, which is an Egyptian cotton, fantastic material for blocking the wind. And we wondered why in the world were these tents basically discoloring and shredding to pieces. And we'll talk about that in a little bit. After several seasons in the Antarctic, I began to think that what we were doing was obviously very exciting. We loved it, but I thought it might be worthwhile to try to find or go to a place where we could apply the sorts of things that we did and were about to do that would be applicable to humans. After all, Antarctica doesn't have any native population. There are almost no animals except in the surrounding ocean. So if you want to go to a place that has ice and people, you go to the Himalayas. And of course, in the Himalayas, there are close to 90 or 100,000 glaciers, depending on how you count them. There are billions of people. About 15% of the Earth's population actually is in that general region. And the biggest and most important thing to them is water, clean water and available water. So we decided that we would like to begin to do more ice coring, except in this particular case, in the Himalayas. So how do you decide where to go? It's an immense place. I started looking at books written by climbers. And the one that I was most attracted to was Fanny Bullock Workman. She ran expeditions from the late 1800s into the early 1900s. That's her up in the left. with her colleagues, all obviously very sprightly dressed, 1904, but they're at about 20,000 feet up there. So I decided that we should go to the same place. It's in Ladakh in the very northwestern corner of India, right on the border with Pakistan. And of course, the first thing I did was start to look at satellite imagery, but there wasn't much satellite imagery there, number one. In addition, every place we wanted to go, in particular where she had gone and we thought would be a good place, was covered in clouds. However, we started out on our way, and as it turned out, before we started, and this was our second expedition into the Indian Himalayas, we already knew that we would not be allowed to carry any maps at all, and we would not be allowed to carry any form of communication, despite the fact that we'd be gone for about 2.5 or 3 months. And we ended up going through magnificent towns. This is in Kashmir, a Muslim area, and obviously water is very important to people here for drinking, for agriculture, for washing in, and it's a very sacred thing to the people, the Hindu people, the Buddhist people, and the Muslim people in this region. As you go higher and higher into the Himalayas, the roads get narrower and narrower. You can see a little slice in the mountainside here. And eventually you get up to the Zojila Pass, which is a little bit over 15,000 feet. And this is where the very fertile plains of the Indian region really turn into much drier, more Tibetan plateau-like country. People who live in this part of the world, and when we were there, were most attracted by the Ayatollah Khomeini. So we had to be very careful about where we went, what we did, what we said. But we eventually got very close to the place where Fanny Bullock Workman had gone. And these were the people who greeted us when we got there. They were sitting on the top of their houses, and they had very, very little interaction with tourists, Westerners. It was pretty exciting to see them. They only had access out of this village and back in for about 3 or 4 months a year when it was snow-free, and they definitely were living a subsistence culture. I was fortunate enough to be able to round up a few of them to help us carry our loads. We all carried very heavy loads into the region that we wanted to go, and I very foolishly thought that they would show us how to go to this glacier. But of course, as we started out, and of course we couldn't communicate with it, we didn't have a common language. I realized these people are farmers; they're subsistence farmers. Why in the world would they want to go onto the glaciers for any reason at all? So, but they were an immense asset, and we had a wonderful time together. We eventually got to the glacier we wanted to go to, and something appeared that I hadn't found in the book that Fanny Bullock Workman had written. 3 very large 500-foot high ice falls that we had to get up and over to get up to that white plateau, which is close to 20,000 feet. We made our way up there, and by the time we got up to the site we wanted to work, we had been gone from home 6 weeks already. Going up that last bit before the plateau, there were a lot of avalanches. We had to stay off the slope when it was warm because of the avalanches. We were working in a place that, because of the altitude, had about 50% of the oxygen at sea level, all carrying heavy loads. And it was so hot during the day from the sun temperature and from the reflection off the sun that we actually had to set up tents, get out of the sun from about 11:30 to 2:30, and then go back to work after that because you could barely breathe despite the fact that you were half the time on a glacier. We eventually made our way up and crested onto the plateau. And this is the sort of view that we got, looking southward down these very large glaciers towards India, or we were in India, but into the Indo-Gangetic Plain. As clouds are quite amazing, and many days we'd be high enough up so we could actually see over the clouds. And what we were most interested in doing was trying to come back with a record of what's called the Indian monsoon. In the summer, air masses come from the south off the Bay of Bengal and off the Indian Ocean, and they bring moisture to the Himalayas, most definitely throughout entire India. That's the reason for their abundant agriculture. And then in the winter, the winds turn around and they blow off the Tibetan Plateau, which is high, cold, and dry. And we hoped that by drilling an ice core there, which we were successful doing, we would be able to contribute to the understanding of this seasonal phenomena that in some seasons brings too much water into India, and the Himalayas, which causes extreme flooding and loss of life. And when, in fact, the summer monsoon is too weak, there isn't enough water for agriculture. I'd like to say that we solved the problem. We didn't even come close. Everybody is still looking at it, but we did end up doing something that turned out to be a big turning point in the way we think about things. And clearly, there's been a lot of work on the monsoon since then. We know much more. And that big thing turned out to be a day up at 20,000 feet, just walking away from our camp, and I could see air masses in the form of clouds, so I could identify them, but it was very strange. They were coming from both the north and the south, and because they were up high, they were snowing. So you can actually see at the person's feet here that this is very fresh snow. We waited for the snow to stop, and then we went from 20,000 feet down to 10,000 feet, collected the fresh snow, came back up to camp at 20,000 feet. And the goal was to see if we could prove something that we all understood intuitively, but we weren't actually sure it would work. Can you actually look at the chemistry of snow and tell where that particular air mass came from? Well, the answer was yes. The chemistry was perfect. We got a cold signal, a dusty signal, a dry signal from the Tibetan Plateau. And from the Indian Plains to the south, we got a warm signal, and we got more sea salt, not a lot of sea salt, but sea salt, and a lot of products of agricultural activity. This was a very, very powerful statement. So this is 1979, 1980. In the last few years, NASA has put this image together. If you look in the upper left, you'll see the clock ticking by. This is 2008 in August, literally minute by minute. And these are a whole series of satellite images that have been pieced together. And what they've done is to colorize the cloud patterns. And they've only put one color per cloud, but in fact I'll tell you what they are. That orange thing that you see going through the equatorial and tropical regions is intended to represent Saharan dust. And there's much more in that air mass besides Saharan dust, but you can only really put one color in. Look at it carefully, and you'll see that Saharan dust makes its way all the way across the Atlantic into the Amazon. It's got a lot of iron in it, so it fertilizes the Amazon. It even makes its way into southeastern United States. If you look a little farther down, the green are places where biomass burning is occurring for Amazon and parts of Africa. If you look around Antarctica, you see these blue swirls. They're supposed to represent sea salt spinning around, and that sea salt is taken inland in some instances. And if you take a look up around the southern part of Greenland, you see that whitish, bluish swirl that's coming off both North America, mixing with Eurasia. That's intended to represent pollution, things like sulfur and nitrogen in the atmosphere. So in fact, if you had more than one chemistry in an air mass, you could actually see where it traveled, and you could document many different things. And that's been an extremely important component of everything we've done since then. Now, the reason that you want to be able to fingerprint air masses is that they transport heat, they transport moisture, they transport pollutants, and they have an impact on surface ocean currents. So not only can you tell where the pollution might come from, but you can also determine, as we all know, if you live in the Northeast and the air comes from the South, it's going to be warm, and vice versa. So we can piece all of these things together, calibrate them with the instrumental records that we have, and begin to develop very detailed stories about how the climate has changed. So around that time, the early 80s, of course, the big environmental issue was acid rain. And as has occurred over the last few years, there were skeptics about whether or not acid rain was actually produced by humans. So we were fortunate enough to be funded by the Environmental Protection Agency to go to Greenland to be able to determine or demonstrate whether or not the pollution coming into Greenland had always been coming in like that. Was it maybe not pollution, but natural? Or did it have some relationship to what people had been measuring for the emissions of nitrogen and sulfur in the atmosphere? So because we found us out in South Greenland, we worked with some Danish colleagues, and because we were interested in recovering an ice core that would tell us about pollutants that come out of fossil fuels, that come out of tailpipes, things like that. We couldn't use a generator. So it was one of the first times that solar panels were used in order to drill an ice core. We didn't want to pollute the area. We wanted to see whether or not it had been polluted. And we drilled down to about the year 1700, did a lot of detailed analysis back in the laboratory. And yes, absolutely, we could see the onset of the Industrial Revolution with marked increases in sulfur in particular. The only time there were increases in sulfur prior to that were during volcanic events. Those give off sulfur. We could see as of about the 1930s, when automobiles become really widespread, a dramatic increase in nitrogen compounds, and both of these tracked what was known about the emissions in North America and Europe. So yes, it was done by us. Much of the acid rain pollution. But what was even more exciting is we've been back there since then, and we've been able to show that the Clean Air Act works. It reduced acidity or sulfur and nitrogen in the atmosphere, which is very, very encouraging. Oops, let me back up again here. So our next step, because we were successful in Greenland with this, was to see if we could find a place in Greenland where we could drill a really deep ice core. Maybe the longest ice core that could be recovered from the Northern Hemisphere. And if we were lucky, we'd get a lot of continuous detailed information. So we spent the next 3 or 4 summer seasons either skiing around or snowmobiling around. And then when we got fancier, we got bigger vehicles and drilling ice cores, trying to understand what the variability was in the chemistry over the ice sheet. But we were also producing ground truthing for aircraft that would fly over for radar surveys to determine what the ice thickness was. And they could hone in on us and know, and we could tell them exactly where we were so that they could add that to their flight path information. And in the process, I ended up becoming the chief scientist and organizer for this large program in which we recovered the longest annually resolved record ever recovered. It came from where that star is in central Greenland. We drilled right down to bedrock, a little bit more than 10,000 feet. It took us 5 summers, 3 months per summer. We built that dome along with logistics colleagues. We built shelters. You see the drill tower there. It was a major operation. There were about 50 people there at a time. And what we did was to develop a record that absolutely changed the way we look at climate change. There were 3 things that we learned, actually many, and I'll just focus briefly on these 3. How do atmospheric circulation patterns change when the climate warms, as it is right now? How fast can climate change, and how small a change is important? So the first thing we learned, because we know that we were looking at very cold periods and generally warm periods, is that whenever it was cold, if you look in the upper left, that's a reconstruction of how large the ice sheet was over North America about 20,000 years ago. We could see that the westerlies, and if you look at this dark arrow, these are the westerlies, air masses that basically move from California over to the East Coast. We know that if you fly from California to the East Coast, it's faster than going the other way around. These are very strong winds. And we learned that when the ice masses get smaller, in general, when the Arctic gets warmer, what happens is the pattern of this, it's called the edge of the polar vortex, the jet stream, becomes much more irregular. And I'll talk more about this in a couple of minutes. But this was a very big finding, to be able to prove that using these air mass reconstructions. Students, everybody spent tons of time either drilling or cutting this ice core up, dividing it up into pieces, sending it back to laboratories. It was a very long process. The most important thing that we did for this project was to see whether or not this little figure in the upper left, one of the few figures I'll show you, that goes back about 110, 120,000 years, that shows you the changes in temperature, zero is basically today. These are temperatures relative today. The coldest part of the Ice Age was about 8 degrees centigrade lower than today. And you can see that, yes, the temperature goes up and down, but you can see also that the ups and downs take hundreds, if not thousands of years. This is a very important message prior to our finding in 1992, because if the climate operates this slowly, that means that pumping, for example, greenhouse gases into the atmosphere probably won't have an effect for hundreds, if not thousands of years. What we found was quite different. We found in the detailed record, year by year, season by season, that there were very fast and very frequent changes in temperature and in storm patterns, and in precipitation. And although it's hard to tell from this particular figure, these occur in some cases in less than 2 years. So the climate is changing faster than a political cycle. And once it made that change, it very often for decades, if not for hundreds of years, sustained that new level, either colder or warmer. And this is called abrupt climate change. We made a lot of newspapers and films as were involved in a lot as a consequence of this, but it really wasn't until 2004 that it began to take off, when Hollywood produced The Day After Tomorrow, based on an ice core drilled, I think, in the Antarctic, should have been in the Arctic, and they talk, of course, about a rapid storm that covers New York City in tens of feet of snow in a matter of days. And of course, they got it the wrong way around. For today, it's quite the opposite. It's not larger ice masses, it's getting warmer, but they did pick up on the fact that this could happen really fast. And this was the first really public demonstration outside of what we were doing that actually showed that the climate could change faster than a political cycle. And the big question they asked is, where will you be when this happens the next time? And we'll find out. So the other question we answered was, how small a change is important? And the answer is, it depends where you are and what you are depending upon. One of the most dramatic changes of the last 11,000 years, which is pretty much the time when climate generally looks the way it does today, was 4,200 years ago. And this was the Mesopotamian Empire. It was a very extensive urban complex in modern-day Syria and Iraq, and it literally disappeared in a few years. They ran out of water. The air masses that brought water to that region shifted, and that was the end. And in fact, many people believe, and I do too, that part of the underpinning for the Middle East war was, of course, the fact that drought hit that region, and subsistence farming, subsistence life, obviously is impacted dramatically if you don't have water. In the case of Mesopotamia, the entire civilization disappeared. Same thing happened in South America around 900 AD to the Mayans several times. And notice these are other parts of the Northern Hemisphere, not just Greenland, but by linking an understanding of the air masses, calibrating with modern air masses, you can see what happens. If you know what happens in Greenland, to some degree, you know what happens in Europe and vice versa, and on your way down. And then around 1000 AD, another abrupt change occurs. It's relatively mild. Eric the Red leaves Iceland to look for new land. He colonizes southwestern Greenland. There are Inuit people living there, but they never really learn from the Inuit, and because they get resupplied every single year from Iceland and from Scandinavia with the way they normally lived, all of the things that they needed. But by AD 1400, plus about 10 years, the climate shifted rapidly again, and the cathedrals and the homes that they lived in were abandoned because sea ice locked Greenland in, and they could no longer be resupplied from Europe. So turns out that these abrupt climate change events can occur for a variety of things in the natural system, and greenhouse gases are part of it in the natural system. But if you take a look at this plot based on an ice core, not ours, you can see that for the last 800,000 years, that red line shows you the range of variability of CO2, and there are other greenhouse gases too. And then all of a sudden, a few decades ago, the levels begin to increase by where we are now, more than 1.5 times higher than anything in the last 800,000 years. And perhaps what's even more important, or as important, is the fact that it has risen in these last few decades 100 times faster than it ever has in the last 800,000 years. So all of a sudden, you have one of the things that in the past contributed to abrupt climate change, all of a sudden being such a dramatic change that it could potentially trigger an abrupt climate change, much less, of course, doing all the other things that we know about. So this is the software that we make publicly available. It's called Climate Reanalyzer. You can do a lot of things with it. And what it allows us to do in this particular case is look at global temperature for a time period, roughly the last 15, 20 years, compared to the roughly previous 20 years. And we can see where warming has occurred and where it hasn't occurred. Notice that there are some blue places which is cooling, and that cooling is mostly over the Southern Ocean because the winds have increased in those places and they've drawn the warm surface air away, water, allowing the cold lower water to come up. But in general, you can see that it's the Northern Hemisphere that's received the greatest amount of heating. And of course, we know what's happened in the Northern Hemisphere. You see that reddish hot spot there, 5-6 degrees centigrade. We know that Arctic sea ice, here's an example, a static example, 1980 September versus 2016 September, which is pretty close to the minimum of sea ice extent. Dramatic difference. And it was suggested back in 2010 that this might happen. And then 2012, 14, they said, well, you know, maybe it'll happen by 2040, 2025, and bang, all of a sudden it happened. So why did it happen so fast? It's what we call polar amplification. If you have sea ice or snow covering a surface, it reflects, in some cases, 100% of the incoming radiation. So if you walk out of your house with snow cover right now, and then you walk onto grass, you'll feel obviously colder on the snow because it's reflected the radiation. It's not radiating. If you remove, in the case of sea ice, because remember the Arctic is a region in which there's an ocean surrounded by continents, and that sea ice is not that thick in general, maybe 3 to 10 feet. So if you could melt that away, what you end up doing is creating a dark surface which absorbs incoming radiation and also gives off all of the heat, not all of the heat, but gives off the heat that would normally be trapped under that ice. So the net effect is that the Arctic warms about 3 times as much as the rest of the global in general warming. And if we focus on one particular event, 2007 to 2012, a 5-year period in which the Eastern Arctic, the Russian Arctic, experienced temperatures as high as 5 to 6 degrees centigrade higher in that one time period. In 5 years, the temperature went up basically 1 degree centigrade annually, not just winter or summer, but for the mean annual every single year. And in terms of its speed and in terms of its magnitude, it is equivalent to the abrupt climate change that occurred at the transition between the end of the vestiges of the last ice age and modern day climate. It is the abrupt climate change that we first discovered and got so excited about. The only difference is that that was over a much more extensive area because there was a lot more sea ice, and therefore the temperature effect was over a much larger area. But this is the beginning. So what was asked in the advertisement for the day into the day after tomorrow is when will the next one occur? Well, guess what? It occurred 2000 to 2012. It's the first abrupt event of the modern era. So what does that mean? Obviously, we know that the Arctic regions are colder, but now what we're seeing is that they are less cold. And we know that the continental regions of the Northern Hemisphere are warming, but the warming in the Arctic relatively is at least 3 times more. So the net effect is that if you decrease the temperature gradient between the Arctic and the mid-latitudes, you weaken the barrier that separates them, the jet stream, the edge of the polar vortex. And if you weaken that barrier, you can get cold air masses pushing significantly farther south. And then you can have cold air masses pushing farther north. And remember, wherever the air goes, heat and cold and warmth goes. storms go because you get warm air and cold air coming together. In some cases, you get drought, you get flood, and it can intensify fires. I'll just show you one example. This is a remarkable example that started occurring in about 2013-14, a few days every year. This particular example, this is the shape of the jet stream, this orange and red pattern that you see here. That red arrow shows you warm air making its way all the way to the North Pole, December 30th, the middle of winter, absolute darkness at the North Pole, and the temperature was above freezing. And this happens more and more frequently now. It's not that it lasts for a long time, but all of a sudden you have these air masses beginning to push against each other, which creates storms. And if it occurs in, for example, an area that's dry already, if a fire starts, the winds are stronger and they're intensified. So the next thing we wanted to do was to look, we'd already discovered a lot of pollution all over the place. We wanted to find out, what does the natural atmosphere really look like? So we wanted to go in search of the cleanest place on Earth. And to do that, we decided to go to Antarctica. And again, we started traversing. We didn't want to contaminate where we were, so we drove couple of 100 miles outside of South Pole into the interior plateau. And then we started skiing, and then we started walking. And eventually we got to a point where we then put on our clean clothing so we wouldn't pollute the sample, and we collected samples. Another place that we worked, not just surface sample, another place that we worked, we dug a snow pit that you see on the right side. It was minus 52 degrees centigrade. It took us 4 days to dig this snow pit and to sample it, literally centimeter by centimeter. I think it was 560 samples. It took us back to the early 1900s because there's very little snowfall here. And what we discovered, the ozone hole by then was well known. By then, we realized that the reason our tents were falling apart was because of the ozone hole being depleted and therefore allowing more UV radiation to come in and have its impact. But what we were able to do with this snow pit was to show that the big ozone hole that was being examined, discovered in the early 80s, did not exist prior to that, certainly back to about the turn of the last century. Now, that doesn't mean that there's not variability in the natural system, but we were able to support what was being seen, that this large an event was not part of the natural variability, certainly of the last 100 years or so. The other thing we discovered, we got here about 18 months after the Chernobyl nuclear accident, which of course happened in the Ukraine, in the Northern Hemisphere, and people hypothesized, could the Chernobyl fallout make its way to the Southern Hemisphere? It can if it goes high enough and it gets transported in the upper atmosphere. And we found evidence of the Chernobyl nuclear accident 200 miles from the South Pole. So if people, I mean, it's just remarkable how far things can travel and how robust a record. And I like to say snow and ice doesn't lie. It just simply tells you what's in there. So that made us think even more about what we could do in Antarctica and the Southern Ocean, for which there was very little information, an immense place, literally only 7 or 8 meteorological stations. It's like having 7 or 8 meteorological stations for just the United States. Southern Ocean that has tremendous productivity in it, an ice mass that if it melted completely would raise sea level 60 meters. Greenland would raise sea level about 1/10 of that. So there was a lot to be learned. And I decided that it would be what we knew it would be an immense undertaking. We knew that one country couldn't do it, so I organized 21 countries, and my wife is an artist. She's always very embarrassed when I show this, but this is what we imagined, that we would get a couple of heavy vehicles, and we would drag sleds and fuel, and that's exactly what we ended up doing. And it turned out to be 21 countries, the International Transantarctic Scientific Expedition. We went all over the ice sheet. The US program that I led on the ground, we covered about probably about 6,000 or 7,000 miles, moving at an average rate of about 3 or 4 miles an hour. So we were in the field many seasons and for a long time. And we were going through areas that had never been gone through before. This was our our crevasse detector. We were dragging 100,000 pounds behind us. And we only had about 100 feet to stop in if we in fact detected a crevasse. We never went in a crevasse, but we were very fortunate. And those white boxes you see have ice cores in them. So we would exchange fuel. We could only drag so much weight. We would exchange fuel for ice cores as we went along. We had some pretty exciting storms. Some cases, that's a Caterpillar tractor halfway covered in snow. Spent a lot of time digging ourselves out, moving forward. We had, all of us were collecting ice cores along the way. We dug trenches in which we could do some measurements in situ on the ice cores. Most of the measurements were done back in the lab. And what did we learn? We learned a whole bunch of things along with many other people looking at satellite imagery, doing other sorts of research. We learned that these icy giants that we like to call them, Antarctica and Greenland, were melting. It's not that they're going to disappear immediately by any means, but they were not as timeless by any means as we thought that they were. And the implications for sea level rise, for changes in weather are, of course, there. We also found out that Antarctica is much more polluted than we thought. We found Chernobyl, as I already mentioned. We saw copper coming from copper mining in South America, and we even saw uranium coming off open pit mining in Australia. It made its way halfway around the southern hemisphere, and in 35 years, the levels of uranium increased by 100 times because of this open pit mining. So the next thing we thought we'd do would be go back to the Himalayas. We had been working there off and on, but by then we really became much more involved, along with other people, in what we call water towers, glaciers that trap water and have it available for melting in the dry season so that agriculture and the ecosystem and humans, of course, can continue. And the most iconic place in the Himalayas is Everest. It's called Chomolungma in China. It's called Sagarmatha in Nepal. There are two ways to get in. You either go from the north through the Rongbuk Glacier, or you go from the south through the Khumbu Glacier. The first ascent of Everest by Hillary and Tenzing Sherpa was from the north, and we chose it because it is iconic. And if you come from the north, you fly into Lhasa, the capital of the Tibetan culture and the Buddhist culture. And from there, you drive quite a few days, and you get to low base camp on Everest. And this is a view of the north side of Everest. And the feature you see in front of you is a stupa. There's a small monastery there. And with our Chinese colleagues, we drilled an ice core up close to 7,000 meters, spent several weeks up there drilling it, and then brought it home. The other thing that we did recently, I was approached in 2018 by National Geographic and Rolex to organize and direct their Everest project. And one of the big questions that we wanted to answer is the highest glacier on Earth actually warming? We know that warming occurs at the two poles. We know that it occurs throughout all of the surface of the planet. We know that the ocean is warming in many places. Does it go all the way up to literally the highest part of the land on the planet, top of Mount Everest? So to get to Everest from the south side, you go through Kathmandu, beautiful old city, make your way up. We flew in part way, and then we have yaks to help us and a lot of people. This was a very big project. If you look carefully, you'll see a bunch of orange and red features. Those are tents and shelters. This is base camp at about almost 18,000 feet. And it has close to 1,000 people in it during the climbing season. Very busy place. This is a close-up of base camp, 53, 54 meters. In some cases, if you try to climb Everest, the cheapest you can do it is probably on a $50,000 expedition, and some of the expeditions go up to $250,000. And at base camp, they have TVs It's quite fancy. The Sherpas who help all of this are amazing. They literally carry all the loads. There are certainly some climbers who go up, carry their own, and go up without oxygen. But basically, this is a major industry for the Sherpas in the area, and they're remarkably, well adapted to this, obviously physiologically, and just wonderful, strong, and wonderful people to deal with. This is a night shot from a ridge above base camp. You'll see the lights down at the bottom, the yellowish lights, and you'll see lights going up the Khumbu Icefall. When people start to train to go up Everest, they go up and down the Khumbu Icefall a few times. That takes you up to about 64 or 6,500 meters. And to get through the Khumbu Icefall and up to the next place that you camp, you really need to start in the dark. And those are headlamps that you see. The Sherpas have put up ladders to get across. It's a dangerous place to go through. The big advantage you have, of course, is that there are a lot of people helping you other than in many other remote areas, but it's a formidable challenge. And then climbing up. And then once you get to about 7,000 meters, people start to use oxygen. And they, of course, wait up here for a little while. And then by the time you get up to, this is close to 8,000 meters. Actually, where that red arrow is 8,020 meters. And the tents are down just below 8,000 meters. And this is, from here up, is what's called the death zone. The yellow and the red area is where our team, I was not part of this particular team, collected an ice core, and the yellow is where our team recovered put in an automatic weather station. And I'll just briefly talk about those, because the answer to the question that was the most important question for our expedition in whether or not the highest glacier on Earth, this is 26,500 feet, there's no glacier on the top of Everest, this is the last flat surface where there's a glacier, is it affected by warming? And you'll see that they're drilling, they're all wearing oxygen. This is a hard place to work. There's about 35% of the oxygen at sea level, that is at sea level. And so you're already stressed, much less trying to work. They drilled a 10-meter core, and we radiocarbon dated the surface, which turned out to be ice, not snow, not compressed snow. And that surface is 2,000 years old. And then we were, without going into detail, able to demonstrate that about half of that glacier, thickness of that glacier, had disappeared in the last few decades. So the answer is yes, resounding yes. That even the highest glacier on Earth is being impacted by human activity. And then at a slightly higher site, this is 27,500. There was an automatic weather station put in. This was the highest they could get that year because there was so much crowding on Everest and so little oxygen available because it all has to be carried up. They had to stop here. But with this, they put that weather station in, and they have been able to demonstrate that the models that are used to predict what the weather is like up there were actually pretty decent. And that's very important because climbers live or die depending upon the wind speeds, upon the pressure. And then 3 years later, after COVID, this station lasted, but they were able to go up, repair this station, and put one almost at the summit of Everest, for which the information is just about to come over. Also had a lot of work going on significantly lower than base camp and also at base camp, drilling the glacier there and collecting water to look at water quality, because as the glaciers melt, they begin to give off all of those pollutants that have been accumulated for hundreds of years as a consequence of our activity. So since we were already looking at glacier change and water quality, water availability in all these other places, we also started to go to the Andes in about 2008. We decided to start, unfortunately, at the very tip of the Andes and the Cordillera Darwin. This is probably the windiest place on Earth. This is where the undeflected winds that go around Antarctica howl around Cape Horn, and we were up at about 6,000 feet on Cape Horn. We went there by fishing boat, and when the fishing boat took us to the edge of the glacier, we had to go up by helicopter because we had so much equipment. As we were landing, the helicopter was being blown around, and we got out of the helicopter, and then we spent the next 17 days in our tents and or digging out to keep from being covered by the snow when the winds gusted up to 100 plus miles per hour. Fortunately, the wind stopped for a little bit, and the helicopter was able to bring us back down to land. But we spent 17 days up there, lost all we were able to recover from the helicopter were ourselves. The pilot in the middle was an amazing guy. He pulled everything out of the helicopter, wouldn't let anybody else fly with him up. He wouldn't let his crew come along. Over torqued the rotor and the transmission and the engine, so that when we landed back down here again, he said, he got us safely back, but he couldn't take us home. So we waited there several days for boats to come with no shelter, which was at that point just fine. We slept in garbage bags for a few days and waited for the fishing boat to come back. Well, the next time we went to the Andes, we were a little smarter. We went to a less windy place. This is in the Chilean Andes, but the glaciers are disappearing fast up here. And we got an ice core and understand we can actually monitor changes in things like copper that are being emitted in the area. We came up with a climate record. And then just this last August and September, we drilled on the highest tropical glacier in the world. It's in Peru. We were not the first people ever to drill there, but we are the first people to be able to utilize a new technology that we have that's going to give us, we think, literally seasonal, if not storm scale, understanding of weather and climate going back at least 2,000 and not 3,000 years, which we hope is going to be very exciting, because this is a region in which civilization has existed for at least 5, if not 6,000 years, including metallurgy, mining. So it could be a very exciting place. We've also been working in the Southern Ocean on the islands where the glaciers are melting fast. We go down there by sailboat from the tip of South America and sail up to the islands, and it can be pretty bumpy, 60-knot winds, sometimes 60-foot seas. This man in orange is the most famous blue water sailor in the world, Skip Novak. We're fortunate enough that he owns a boat and he's the captain. Come across these amazing icebergs. Not only are they colored, but they're also scattered with penguins. It's just a superb area, whales. And then once the sailboat's gone in as far as it can, we go in by Zodiac. And this particular trip, we went to South Georgia, and that arrow points into what's called King Haakon Cove, which is where Shackleton ended up after his remarkable open sea voyage, trying to find a ship to come back and save his crew. And then he walked across this red path and ended up in the place called Stromness around there, and eventually found a vessel to go back in 1923 or 4 to save his crew. So we did exactly the same traverse that he did, except we did it in order to be able to drill into the highest part of South Georgia to see if we could get a good ice core record. And the answer is that the upper surface is melting fast, but we will try to go back there to actually drill down. It's a complicated place to go logistically. Helicopters are not allowed there. This is our team that did the Shackleton traverse and recovered the ice core. The other place that we've been working is Europe, on the Swiss-Italian border, the picture to the left. And you can see Saharan dust gets into that area in the star. So we have a 2,000-year-long record of Saharan dust behavior. We have a record of pollution, but one of the more interesting records that we have, because we work with historians at Harvard who have remarkable written records going back a couple of thousand years for this region, we were able to identify the Black Death, which of course was a remarkable pandemic. Terrible, half of Europe, if not more, died. And we identified it because the levels of lead in the ice core dropped down to almost 0. Now, lead, we all know, is not a healthy element for a variety of reasons: cardiac disease, nervous disorders, cancer. And the health standards for lead are based on the pre-industrial levels. What we found, however, that lead in Europe and Asia has been emitted for close to 2,000 years. Not as high levels as recently, but nevertheless. And we found that because during the Black Death, when so many people died, there was no more smelting. There metal, and people had more important things to do than worry about making coins and weapons. The other thing we did was work on the 1918 pandemic. We discovered in this record that something you can't tell from the instrumental record, that 1918, the end of World War I, the swine flu, when 50 million people perished, this was a particularly wet and cold period compared to the previous 60 to 70 years, which goes well beyond the instrumental record. So we were able to say a little bit about the economy from the lead, about health from lead, and also about the conditions that tend to worsen in this particular region, pandemics. As of 2022, we've been sailing another vessel, another sailboat up along the coast of Greenland. Our goal there is now that Greenland is beginning to melt, as indicated by the blue area, that's number of days of melt per year. The red area is where it's melting the most. And what's particularly, and as it melts, of course, pollutants that we've been putting in there are melting out, getting into the ecosystem and getting into drinking water. What's particularly interesting from our point of view is that red star shows where we drilled down to the base of the Greenland ice sheet and discovered abrupt climate change. And when we were there, there was no way there was any melt. And now not only is there melt there, but it rains on occasion in the summer. So that's only been 30 years and it's changed so remarkably. And this is the sailboat, slightly smaller, that we use to look at Greenland glacier meltwater. And here's an example of what we did in 2022. We measured lead in marine water, in streams, on ice edges, and we actually found some places where the lead levels are beyond what the World Health Organization says are healthy. And we're going to continue to do this up and down the whole coast of Greenland for not just lead, but for many other measurements that we make. So to wrap this up, climate change can operate faster than a political cycle, something we did not even believe before. Atmospheric circulation patterns are changing, and that's because of differential warming, causing air masses to have patterns that they normally don't have, much more extreme weather. And we also learned, which we should have known, that what we put into, in this particular case, glaciers, comes out. We've come full circle. We've loaded these glaciers, particularly in the Northern Hemisphere, with tons of pollutants. And now, of course, they're coming out, and what sort of an effect are they going to have? And I'll leave you with this final statement. The age of climate decision is here, and our actions will define the course of civilization and the health of our planet. Thank you.
Thank you, Paul. Fascinating and terrifying.
Well, hopefully somebody will ask a question, how terrifying is it? And I can
That is definitely within the range of questions I have so far.
Okay.
So one of the first questions, and I think Professor Mandia answered it in the chat, it was a question about the jet stream and seeing if you could comment on just that understanding of the jet stream moving as a result of climate change.
Sure. As you begin in the case of the Arctic, to warm the Arctic, the temperature difference between, let's say, what it was when 20 years ago, when the Arctic was as cold as it typically is, and today the temperature is warmer in the Arctic, not everywhere, but in many places. So the net result is that you have a weakened temperature gradient. When you have a weakened temperature gradient, the winds tend to run along, not quite lines of latitude, but pretty much west-east. And if you have very cold Arctic and very warm mid-latitudes, the temperature difference is very sharp, and the net result is that the winds actually pretty much go west-east, not exactly. But the bottom line is, when you weaken that temperature gradient by warming the Arctic, the net result is that you can have cold air masses pushing farther south, warm air masses pushing farther north, which is the example I gave, because the barrier, the edge of the polar vortex, the edge of the jet stream is much weaker, and because that barrier is weaker, air masses can go back and forth and they can meander more. But the big question is, and not everybody believes that statement. I do, because we've proven it in different ways to ourselves. But the bottom line is, we are getting less stable weather than we've had before, not only on a daily basis, but from year to year. We're getting not only more storms, but more drought, and it has to do with where the air masses are and what water surface temperatures are.
Thank you. AC had a question whether or not you were able to see any detection of short or long-term climate impact from major volcanic eruptions.
Absolutely. That's a great question. Yes, in fact, there are obviously historically known volcanic events. We can detect them from high levels of sulfur, bismuth, and various other chemistries that we look at. And we know, for example, the Pinatubo eruption of 1991 to 1992 put so much sulfur in the atmosphere that it cooled much of the northern hemisphere 1 or 2 degrees centigrade for a year or two, depending on where you are. So we use those known historical events from the history record to make sure that we are counting year by year correctly. And then when we get down to the very old volcanic events, we find some very interesting things. There's an event that occurred called Toba that occurred 72,000 years ago. It pumped so much sulfur into the atmosphere that it cooled the climate for 100 years. It is in effect an analog for what a nuclear winter would be.
Julia wants to know if you can comment on Canada's Columbia ice field. Have you or others sampled there?
Yeah, one of the first places I took undergraduates when I was a young assistant professor with the Columbia ice fields. They've obviously, it's a very neat place because, as I'm sure the person who asked the question knows, they've marked where the former ice positions used to be. It's getting smaller and smaller. And as it begins to get smaller, obviously there's more and more melt. And just like Everest Base Camp on the Khumbu Glacier, there are more and more streams that are running over it, within it, and under it, and it's becoming more and more of a cheesecake. In the case of the Khumbu Base Camp for south side of Everest, all those places that people were camping are basically a honeycomb underneath them. And they're thinking now of moving the base camp because it's going to get more and more dangerous to be sleeping on it.
Larry has a question about dating the ice core, and I'll add my little piece to it too. You had mentioned radiocarbon dating of the ice, and I was wondering what materials are actually available to do that in where you were doing it. That was interesting to me. But Larry more specifically wants you to know if you could briefly explain just the process of determining the age of an ice core and then identifying the contaminants.
Important question. I'll talk about the carbon-14 in a second. But what we do is we try to count year by year back through time. And we do this by looking at seasonal variations in the chemistry. So, for example, if the summertime is when maritime air masses come onto the ice sheet, there should be a sea salt, dominant sea salt summer signal. And we can see that very easily. So we count the number of sea salt spikes. And now we have new technology. Typically, in the past, we were only able to do 1 centimeter resolution. That's 100 samples per meter. Now we're the only lab in the world, and we can do 10,000 samples per meter. So we can not only see years, identify years because we can see seasons, but we can literally identify storm events. And this is all based on seeing that chemistry. So then we calibrate it to volcanic events. We calibrate it to nuclear bomb testing in the upper part. And there are other tests like lead-210 and also radiocarbon. And the best way to do radiocarbon dating, of course, is to have some particulate matter, carbon. But there's a lab that we work with in Switzerland, and they can actually look at the dissolved organic carbon in the ice. And from that, provide very good dates. And this last ice core that we recovered in the tropics in just a few months ago, drilling down, we found within the lower few meters of the ice core, it was 128 meters deep. We found 2 places where we actually identified organic material that had blown in. So we're sending that to our colleagues in Switzerland, and they'll date the organic material, and then they'll date the ice, the dissolved organic carbon surrounding it, which will be even a further calibration if those 2 numbers come out together.
And then one of our student participants, Jalen, wanted to get to your other question, which is how terrifying is this? What is the implications? And there are a few other questions in here that are relating to that in terms of sea level rise and what can we do about it? You know, is there something we can do?
Yeah, well, The answer it is terrifying, but I'm very optimistic about it because we all know that we've gone back and forth a few times, government policy and what the public believes. But I think we're definitely going in the right direction now. We have not mitigated our emissions as fast as we should, without a doubt. The best scenario for the future is probably plus 2 degrees centigrade by 2100. If we were to flatten emissions out very soon in the next 10 or 20, flatten them out back 20 years, in the next 20 to 30 years, we might see the temperature leveling off a little bit. But the bottom line is that we have, as a consequence of emissions of CO2, we've really bought into some serious warming for the future. The other scary part of it, before I talk about the positive part, the other scary part is, of course, methane, which is 30 to 50 times more effective in trapping heat. Methane comes from grazing animals. It comes from leaky pipes, supply pipes, but the largest source of methane is trapped in the frozen ground in the Arctic, and as that begins to thaw, there could be tremendous amounts. You dig a hole in the snow in parts of the Arctic and drop a match in, it'll catch fire because the methane is trapped under the snow. That would create another super big abrupt climate change, bigger than the one I talked about. So the other negative part is that there are parts of the planet, low-lying islands, people who live in the Arctic, in particular the Russian Arctic, because they have so much permafrost, where it's going to be very hard for them. There will be a lot more refugees from climate than there were refugees from the Middle Eastern War. So why am I optimistic? I'm optimistic because I think we're beginning to do a lot of smart things. And even if we weren't going to have warming, the idea that we're transferring to a renewable energy, we were forced to do it because of this, but there are obviously all of the political and economic values to it. More and more people are working in that industry. I've talked a lot about pollution in ice cores. Well, that pollution is transmitted through the air. 8 to 10 million people a year die prematurely from bad air quality. And if we begin to shut down greenhouse gases, we also reduce those emissions. And for people who are more skeptical about the value of greenhouse gases, I think everybody will agree that we all want to be healthy and we want to have clean air and we want to have clean water. And we do in some places, but we don't in most places. And by cutting down greenhouse gases, being smarter about the way we do things, we could have a much better quality of life in terms of air, which has tremendous, 8 to 10 million premature deaths per year. We lost 5 million people total from COVID. This is 8 to 10 a year. I'm also very optimistic because I think that particularly with the internet, with some of the amazing creativity that's coming out of the most recent generation, this forthcoming generation, we're going to find way more economical ways to function. In a place like Maine, where people spend at least 10% of their salary on energy, we're hoping to have offshore wind power here that would reduce that dramatically. It would give people better jobs. Our economy, there are very few people in our state, 1.25 million, and we tend to lose more than we gain. I personally think that as the jobs get better, which they will, people can stay home now because of the internet. All of these things help climate change, and all of these things together are going to, in some parts of the world, create a better quality of life. We have to be smart about where we go and what we do. We don't want to be building cities in places that the sea level is rising. I'm not saying we should destroy the cities, but the best estimates are close to 90 centimeters, about 3 feet of sea level rise by 2100. But we shouldn't just be thinking about 2100. That's just the beginning of sea level rise for a 2 degrees centigrade rise. By the next 200 to 300 years, we could easily have another 2 to 3 to 4 meters. So understanding what our future is very important for planning, and particularly for younger people who might go into business, who might go into science, journalism, anything. There are more and more ways in which they can contribute to a better quality of life and to mitigating all of these things. So it's wonderful to see the younger generation getting empowered, thinking about this. And I'm very optimistic that there will be many parts, certainly the United States and many other areas in which, despite the sadness in other areas, things will actually be better to some degree. We'll probably be a little bit more careful about, when we go places, we can't necessarily fly every single time we want. We have to watch the weather. But hopefully, if things get a little better for some of us, we'll make it better for other people in the rest of the world. If you live in the low-lying parts of the world, it's hard. In Southeast Asia, where sea level is encroaching in rice fields, there's some remarkable discoveries that have been made with respect to rice. They're now beginning to grow more salt-resistant rice. And so all of these remarkable new approaches, whenever there's a war, it's a terrible thing, but at the end of the war, very often there's some valuable innovations. And I think we have to look for the silver lining. We have to be optimistic, but we also have to keep in mind that, particularly for younger people, their careers may very well be to some reasonable degree dominated by what happens to the climate. So it's important for them to understand what's going on.
So with the warming that you're seeing, how much more time do you think you have to continue the sampling project? Because you mentioned that it was difficult to do it as melting occurs.
Yeah, it is absolutely true. There's a group that in France that is actually going and collecting ice cores and transporting them to the coldest part of Antarctica to store them for the future. We are finding more and more places, particularly in the high mountain areas and coastal regions of the ice sheets, where the upper part of the record is missing, which is where known volcanic events and radiocarbon dating become very valuable. The record below is still okay. And we know what's happened in the last couple of 100 years. So there are still places that we can go to learn things about ancient civilizations, to learn about what people did in the past that might have, how they lived, how their civilization survived or didn't survive. So there'll still be ice coring going on, without a doubt. It's just slightly different than it was before. But we've already done, not we only, all of the people in this business have already done quite a bit, and and there will be more to do.
Thank you. And there's one last question, Paul. It's and this is just curiosity for me and Wendy. Why were you unable to take communication devices or maps in the Himalayas? That had to be terrifying.
Government of India would not let us. There was when we started going there, this was a time when there was a lot of friction between India and the United States, because there was the belief that the CIA was working on the border and observing things. Who knows what was really going on, but there was a lot of tension. So I always had to have an Indian colleague, but interestingly enough, our Indian colleague was not allowed to have a map or any communication either. So it was interesting. But of course, we were all much younger then, never assumed that anything would happen. And we went merrily off and came merrily home, and everything worked well.
And we're glad for you that it worked out. Well, thank you so much, Paul. It's a really interesting talk, and so happy for everything that you've done, just to bring knowledge of this to the rest of the world and everybody in the participation of this talk. Thank you so much. We really appreciate everything you've been doing.
Thank you, Sean, and everybody who listened in. And if anybody has any questions they'd like to ask me, you can find me on our Climate Change Institute website. I'd be happy to talk to you. And some of the software hub people that we have, people might be interested in. I'd be happy to talk to them about that too. It's publicly available. A lot of some of the graphics I showed came directly from that. We get about 3,000 hits a day for some of our software. Much of it appears in mainstream media. But thank you for the opportunity. Have a good evening, everybody.
You too, Paul. Thank you.
Thank you.